Good call. Right, so we're going to talk about rigid body rotation. And apologies if my handwriting is bad. I'm apparently, well, I don't know why. So we've looked at general motion in the past, like how would a projectile move when it does such and such, or if you swing a rock in a circle, what happens? But now we're going to talk about the special case of an object just rotating. Like just think of a solid thing just rotating rather than like a whole bunch of different things moving in their own way. So we need to define what a rigid body is. So a rigid body is kind of exactly what it sounds like. A rigid body is an extended object okay, I have the Roni that rotates as one. And in particular, it has no parts moving, or no parts moving relative to one another. Relative to other parts. Except the motion due to rotation. So a rigid body is basically just what you picture when you think of like a box, or just something that's not like bendy and or fluid or whatever, just like any normal object, like a phone, rigid body. A cup, rigid body. Right, so rigid bodies are most of the solid things that we think of. So I'm just going to draw an example rigid body, this ham thing, and I'm just going to assume that that there's some, maybe there's a hole through it and we like put a nail through it and so it can rotate about that. So in principle, this thing could rotate. It's going to be hard to draw the same thing again. That's close enough, but whatever. Okay, you guys get the picture. The point is it can rotate about that axis. And so if we tracked just a single point, say call it A, if we track just a single point over that rotation, it's going to trace out motion like that. And if we tracked another point, say B, and this is where my poor drawing skills come in, it will trace out motion like that. And so what we can do is we can actually look at how much of an angle each rotation covers, and it should make sense to you that they cover the same angle, because they're rotating by the same amount, right? And so that distance is also theta. So now we can ask the question of what happens, or what, like how these things actually move. Like we can try to quantify it. So what is the motion? And what makes that motion similar? Well, clearly they cross the same angle, but how do we characterize that? So first, keep in mind that typically we use the letter S for arc length that's traveled. So the distance that S travels, we've gone over this when we first started talking about rotation. The distance that S travels is just the distance that, the distance that A travels is just the distance that A is from the axis of rotation times that angle theta. And if that angle theta was 2 pi, then the distance it would travel would be 2 pi r, which is the circumference of a circle. And so from that, we can derive a result. The speed, and this is speed now because the direction is constantly changing. We're just interested in the speed, assuming at any given point. The speed is the rate of change of it's the time derivative of the distance that it's traveled. And that should be fairly straightforward, but if it's not, just think of it this way. Typically, position is just a time derivative of, velocity is just a time derivative of position. Here, we're talking about distance traveled, so the time derivative would be speed. So this is dSA dt. But we know what SA is, so this is the time derivative of RA times theta dt. And the distance that the object is from the axis of rotation is constant. So we can pull it out of the derivative, and so we get RA times d theta dt, or RA times omega. Remember, omega is the angular speed, or velocity if it was a vector, and it tells you how many radians the object travels through, like how many radians, which is how much of an angle does the object travel through per second. And so we can do the same thing with position B. So it's RB times theta is the distance traveled. And so the velocity of B, we could just work it all out. It's all the same, except at the end of the day, we would get that it's RB times d theta dt, which is just RB times omega. And the important point is that because they pass through the same angle, they have the same angular speed or angular velocity. So the takeaway here is that while the linear velocities VA and VB are different for A and B, i.e., in this case, B has to travel faster because it covers the same, or it covers more distance in the same amount of time, they have the same angular velocity or angular speed. And I'm going to use the word velocity here, and I'll explain how this works when we start working with three-dimensional rotations. RA theta is, so just RA. RA is arc length. Oh, no, you're right. RA theta is arc length. Right. So from this simple example, it should be fairly straightforward. I said B covers more distance because it's further away from the axis, right? So when we discuss rotation, we don't really need to worry about where a particular point on an object is, because we can always figure out any of its motion just by multiplying it, like multiply its angular speed by its radius, by the distance from the axis of rotation, and you'll get the translational speed. Multiply the angle or the angular displacement by its radius, and you get the linear or the translational displacement, and so on. So when we talk about rotational motion, the interesting part is not the translational motion, i.e. how far a thing actually travels. What we're really interested in is the rate at which things rotate, how their rotation speeds up, slows down, how far things rotate, and so on. So when we do rotational mechanics, we only actually talk about the angular motion. And that's just because getting the translational motion from the angular motion is really easy. And so if we can characterize the rotational motion, then that's enough. So how do we do this? Well, when we talk about the position, the angular position, by the way, all of these words I'm about to write, you might want to put angular or rotational in front of them in your head. So the angular position is just given by theta of t, where theta is some amount of radians that whatever object we're considering has deviated from some reference point. So maybe initially the reference point is the x-axis, and then it rotates up, and so it would have rotated up theta radians after time t. We can talk about displacement, angular displacement. That would be delta theta, which is the difference of the angular positions at two different times, which would just be, say, theta 2 minus theta 1. We could talk about average angular velocity, put an angular there. That would be omega average, which is just delta theta over delta t. We could talk about the instantaneous angular velocity, which would just be omega of t, which would be the time derivative of the angle, or of the angular position. We could talk about average angular acceleration, rather. So these are all things that we've seen in the translational case, like position, displacement, average velocity. But we're doing the exact same thing, just now in terms of angular motion rather than translational motion. By the way, when I say translational, what I mean is like where we're talking about an object moving, not an object rotating. So this would be alpha, Greek letter alpha. Let me write a better alpha. average, which is delta omega. By the way, this thing is not a W. I don't want to see anybody calling it a W because that irritates me. We could also talk about the instantaneous acceleration, and that thing's not an A, it's an alpha. And the reason, by the way, why we use Greek letters for, the reason we use Greek letters for rotation is just because it helps us, or at least it helps me, and hopefully it'll help you, kind of keep the different types of motion separate, because there's translational motion, which uses Latin letters, and then there's rotational motion, which uses Greek letters. Hopefully that'll help. And so the instantaneous acceleration, alpha, instantaneous angular acceleration, is d omega dt. So all of these things are exactly in like a one-to-one correspondence with what we saw when we were talking about linear motion, i.e. there's all, well, yeah, so all we've done is just stick angular in front of each of these words and then given them a new name. That's all. And so just like, I don't actually know what IE stands for. Something Latin, I think. But it's like for example almost. Or that is. Google it. So just like for linear motion, if the angular acceleration alpha is constant, meaning some amount of radians per second squared, we have kinematic equations for rotation. So remember how we derived the kinematic equations. This is the x of t is 1/2 ax squared plus v naught t, sorry, 1/2 ax t squared plus v naught x t plus x naught. The way we derived that was basically by integrating and by noting that the acceleration was constant. We can do the exact same procedure here for rotational motion. So we would get theta of t is theta naught plus omega naught of t, or times t, plus 1/2 alpha t squared. So notice that it looks identical to the traditional kinematics. It's just we've replaced alpha with a with alpha, v naught with omega, and x naught with theta. That's all. And then you could write down the kinematic equation for omega, which would just be omega naught plus alpha t. And then you could do all of the standard things where you, for example, combine these. So let me actually put a box around these because these are useful. You could combine these. And to get the same kinematic equations that we've seen, like a range-finding equation, you could do the same thing for a range-finding equation for rotational motion. For another example would be the final angular speed squared minus the initial angular speed squared equals 2 times the angular acceleration times the angular displacement. That would be another example. So the only difference between angular motion or angular kinematics and linear motion or linear kinematics is that the distance, anytime that there's a distance that appears here, is measured in radians. So rather than traveling 5 meters, you rotate 6 radians, right? Rather than traveling at 4 meters per second, you rotate by 9 radians per second, and so on. It's one-dimensional because, well, okay, I can explain that later, but I promise that it is. It's one-dimensional in the sense that that you're rotating about an axis and the axis is one-dimensional, is what it boils down to. You can have rotational motion. You can have 3-dimensional rotational motion where you have rotation about 3 distinct axes. That's a thing. Just as a quick aside, so nobody gets confused, centripetal acceleration has nothing to do, or almost nothing to do, with alpha. They're just unrelated concepts. Now, I said that this is technically a type of one-dimensional motion, but I should probably be a little bit more clear about that. So what would it mean for rotational motion to have a direction? Well, so we extend rotational motion, and by extend, I mean like we generalize the idea of this rotational motion that I just described to 3D via the right-hand rule. No, so that's the point that I'm making right now. So if we want to know the direction, like the vector direction associated with a rotation, we curl the right fingers in the direction of rotation, and then the thumb points in the direction of the vector. So the way we associate rotational motion with a vector, so that we can then actually start talking about rotational motion in 3 dimensions, is we basically just associate the rotational motion with the axis about which it's rotating. That way, we actually, like, because every type of rotation has a unique axis about which it rotates. Just to answer Cesar's question, they're just different things. Centripetal acceleration, even though centripetal acceleration is acceleration towards, it's a linear acceleration, meters per second squared, and alpha is rotational acceleration. They're just unrelated concepts. Like I just don't want you to get them confused. That's the only reason I wrote that down. Right, so let's talk about an example. Let's assume that, like, phone rotating this way, right? So what direction would its angular velocity be in? Well, so the angular velocity, we would curl your right hand in the direction that it's rotating. This is my left hand, but it's mirrored. So it's rotating this way. So curling my right hand in that direction, the vector would point downwards. And if, on the other hand, it was rotating like this, actually, that's the same direction. Let's say it was rotating like this, then curling my right hand in that direction, it would point out of the screen. So that's what I mean when I say that we use the right-hand rule to determine the direction of rotation. And then you can see that there's a vector associated with it. We know the magnitude, that's just the rotational speed, for example, and then there's a direction, and hence we can write it as a vector. Similarly, the angular acceleration will have a direction associated with it. Basically, by the same rule, you figure out how much is the angular speed increasing in this direction. If so, then the angular acceleration is in that direction. And angular displacement would also have a direction, because the angle is going to change in, say, this way to this way. So it would, the angular rotation would be out of the screen. So the whole point is that there is a sensible way that we can associate a direction with a vector, and then you can see that if we're only talking about rotation in a 2-dimensional plane, like in this picture, there's only one direction in which that rotation can occur. And so in that case, the direction of motion would be, again, out of the screen, because it's rotating this way. And so in that sense, it's 1-dimensional, because it's only taking place about a single, there are no other pointing axes about which the rotation could occur. Right, so let's, so rotational kinematics is easy. Let's talk about rotational dynamics. So rotational dynamics, just like linear dynamics, or so let me clarify. Linear dynamics was basically energy conservation, momentum conservation, collisions, things like that. In order to study rotational dynamics, we should use the same tools that we used for linear dynamics. So for linear dynamics, we had these tools. We used kinetic energy and potential energy, of course. Kinetic energy and linear momentum. You might, by the way, you might sometimes see me kind of swap linear and translational, they basically mean the same thing. I just want to make that clear. And you might occasionally see me put in the word translational kinetic energy here, just to differentiate it from rotational kinetic energy, because there's a sense that you can talk about total kinetic energy, which is both combined. But when we were doing linear dynamics, this is like collisions and things like that, we used kinetic energy conservation and linear momentum conservation. So in order to do the same type of calculations, in order to do the same type of calculations or same type of analysis, but for rotational motion, we should come up with some sort of analogs of these quantities of kinetic energy and momentum for rotation. And by the way, it kind of makes sense that there's an associated kinetic energy with rotation, right? If a thing is spinning faster, it's harder to stop, for example. It takes more effort to stop. Similarly, if a thing's really heavy and it's spinning at some rate, it would be harder to stop. It's translational. If something's really heavy, it would be harder to stop. Hence, there should be some sort of rotational angular or rotational momentum. Typically heavy things, just like how a heavy truck is hard to stop compared to a light sedan. So we have good reason to think that these things would exist just from our intuition anyway. So let's talk about let's try to derive these quantities. Let's talk about kinetic energy first. So let's work out an example, or I'll just provide you an example how we can build such a kinetic energy, or such a candidate for what the kinetic energy looks like. So here we just have a solid rod, rotating about this axis, say. So if we want to find the kinetic energy of this rotation, one way that we could do it, and that this is just how much kinetic energy does the whole thing have rotating, and it should have some, right? Because there's some amount of mass over here, and that mass is moving, right? So that will have some kinetic energy. And the mass over here will have some kinetic energy, and so on. So there will be some kinetic energy. We just need to figure out what it is. And so what we can do is we can just break up the rod into chunks and then find the kinetic energy of each chunk and add them all together. And that's what we're going to do. So the kinetic energy of the rod in its rotation, we're going to assume that it's actually rotating. We'll get to that. The kinetic energy of the rod is 1/2, say, it's called this one at 1, 2, 3. I'm just ways of labeling the points. M1 times V1 squared plus 1/2 M2 times V2 squared plus 1/2 M3 times V3 squared, and on, right, until we run out. But keep in mind that we can rewrite the speed of each of those chunks in terms of its angular speed. For any speed connected to, or for any rotational motion, the linear speed, v, is related to the angular speed, omega, by multiplying by r. And so this r here is the distance of a chunk. By the way, I love that word chunk. Of a chunk from the axis of rotation. And this omega, this is the same for every chunk. My cat used to be a chunkster. He's not anymore. He lost some weight. And so what we can do is we can do this for V1, for V2, for V3, and so on. And so we find that the rod's kinetic energy is 1/2 M1 times R1 squared omega squared, where omega is the same for all of them. Let's give this rotational speed of omega, plus 1/2 M2 R2 squared omega squared, plus 1/2 M3 R3 squared omega squared, plus ... And so we can factor. We get that this is 1/2 M1 R1 squared plus M2 R2 squared plus M3 R3 squared plus ... times omega squared. And so this thing that is multiplied by omega squared and multiplied by 1/2 We call this thing I. We just give it the letter I for any given object. And it has the name rotational inertia, also known as moment of inertia. So I will use those two phrases interchangeably, but they're the same thing. So what we've learned is that there are two more correspondences to the linear motion case, right? So before we saw that like if you replaced x with theta and v with omega and a with alpha, then you could just take the kinematic equations and just replace them with the rotational equations. So similarly, we have a new correspondence, 1/2 mv squared, which is translational kinetic energy, corresponds to the rotational kinetic energy, which we can write as 1/2 I omega squared. And so the new correspondence that we have, or another new correspondence, is m, which is mass, corresponds with quote unquote rotational mass, or moment of inertia, which we call I. So when we talk about rotation, in all of our calculations, instead of having m floating around, m will sometimes be there, but instead of having m floating around, we have I. Now, just as an aside, there is this correspondence, there is this like explicit analogy that you can build where you just replace all of the translational variables with the rotational variables, and everything will be the same. But there is a little bit of a breakdown that's kind of hidden in what I've just written down, and that's that unlike mass, which is just like a number and it doesn't depend on anything, it just the mass of this thing is what it is. The rotational mass, or the moment of inertia, depends both on the mass of the object, because m1, m2, m3, those all make up the mass, but it also depends on how that mass is distributed and where the axis of rotation is, where the axis about which you're computing this moment of inertia is. And that's important. On mass and where the mass is. So, for example, you could have two objects that have equal mass and equal rotational speed, but they could have different rotational kinetic energy. And the way that could happen is they could have different moments of inertia. Like the mass of one of the objects could be really far away from the axis of rotation, whereas the mass from the other object could be really close to the axis of rotation. And that would change the moment of inertia, and hence would change the rotational kinetic energy. Now, there would have been a demo that I would do if I was teaching this in person, but I don't have access to these. So I guess I kind of have to, maybe I'll after lecture, I'll look for a video and I'll like post it as an announcement or something. But it boiled down, well, no, a video doesn't help either. It boiled down to me passing around some rods that look the same and have the same mass, but have the mass distributed in different ways. And so you can just feel by rotating them that there's some different property about them, even though their masses are the same, their shapes are the same, and so on. Now, what we're about to get into is, I would just call it KE sub R or something. What we're about to get into is, I often tell students, is the hardest part of the course. And that's just because students don't really like to do integrals. Don't ask me why. But so this is going to get pretty math heavy. So bear with me. It'll all be over by either today or Friday, and then we'll proceed. Right, so we're going to talk about how to calculate these things. And we're also going to have to backtrack to center of mass and talk about how to calculate that. So we're going to talk about calculating center of mass and rotational inertia. For given scenarios. So just as an aside, both center of mass, abbreviated COM, and rotational inertia depend on the distribution of the mass. i.e. where the mass is located. And so, but there's a difference between these things. Like center of mass and rotational inertia aren't the same thing. The difference is that well, I mean, there's a lot of differences, but a key difference is that the center of mass is a vector, i.e. it tells you relative to some origin where the center of mass is, which is a directional thing. Whereas rotational inertia is a scalar, at least for our purposes. In general, it's actually something called a tensor, but we're not going to get into that. So in the past, we've seen how to calculate both of these things. So for example, the center of mass position is m1 r1 plus m2 r2 plus ... divided by m1 plus m2 plus ... where each position vector ri is displacement from an origin or from some reference point. And when we calculate moment of inertia, which I just showed you how to do, the moment of inertia is m1 r1 squared plus m2 r2 squared plus ... And again, each ri, in this case they're ri squared, so we don't have to worry about the what direction it's in. This is the squared distance from a reference point. Now, just as an aside, that reference point is usually the axis of rotation. But it doesn't necessarily have to be, especially if the thing's not actually rotating yet. Sometimes it's useful to compute the moment of inertia about some particular point. As another aside, this is not the distance from a point, or let me say from a reference line. Typically, it's not the distance from a particular point in space. It's the distance from a line in space to whatever point. So it's the perpendicular. So like if you have an axis of rotation about which your lumpy thing is rotating, and maybe that lumpy thing is, I don't know, super lumpy. So this point, we would calculate this distance. This point, we would calculate this distance. So it's the perpendicular distance from the line. They wouldn't all be computed from the same point, is what I'm getting at. So you would just pick up, each point you find the shortest distance to that line, and that will be the distance that you're computing. But okay, yeah, I'll repeat it again. So unlike a center of mass, which is displacement from a particular reference point, like you pick an origin and then you figure out where is the center of mass relative to that origin. So the vector would point from your center of mass, from your origin to the center of mass. Moment of inertia, the ri squared, that r represents the distance from somewhere on a reference line, which is usually the axis of rotation, to the point of interest. And it's the perpendicular distance, meaning you would draw a perpendicular line from the point that you're trying to find ri squared for to your axis. So you would never use, say, that line. You would find the line that's perpendicular from your point to the line, to the rotational axis. I promise it's not as complicated as it seems. Now, both of these methods work fine if there's only a finite number of things. If you can break up your object into like 8 different chunks, then you can just add them up and then be done, and you've computed the moment of inertia. But the real question, and what is more useful, is really answering the question, what if there isn't a finite number of point masses? These chunks that we've been talking about are point masses, by the way. And for a real object in the real world, it's just not a good approximation to treat it as if it were just a finite number of chunks. Even though in reality it is a finite number of chunks because there's a finite number of atoms in any given object and so on, that number is so astronomically huge, we just assume that there's an infinite number. And so the way that we handle these is we think back to calculus. So before, we could write the center of mass position as a sum. I equals 1 to, say, n, where you have n objects, and then you have mi, ri. And then you divide by the sum from I equals 1 to n of mi, right? But that doesn't work if you have an infinite number. And by the way, for the moment of inertia, it would just be a sum from I equals 1 to n of mi ri squared, right? But if we have a continuous object, i.e. an object that can't be broken down into a finite number of pieces, then n would go to infinity. And so this becomes an integral, which is what somebody was getting at earlier. So in particular, if we have a sum that looks like a sum from I is 1 to n of mi times stuff, where that stuff might tell us something about like where that mass is or whatever, and maybe that stuff is sub I or something, we could rewrite that in the limit as n goes to infinity as an integral of stuff dm. So when we start breaking down a real object into an infinite number of parts, each part becomes infinitesimally small. And so that's why the m becomes the dm, because the limit of mi goes to 0. So let's try just doing examples. So example, I'm going to write out some words here to illustrate the example. So let's say a rod. By the way, the reason we use rods is because they can be approximated as just lines, because we don't really care about how they're extended in the other direction. So a rod has a uniform density of mass with a mass density, and by the way, when I say mass density, that means mass per unit length. So think 1 centimeter of this rod has such and such mass. 2 centimeters would have twice as much mass. So the mass density would be the mass of 1 centimeter divided by the length 1 centimeter. And so the mass density is given the name lambda, Greek letter. It's just some formula. Like in the case of RCM, it would just be multiplied by the vector Ri. In the case of moment of inertia, it would be multiplied by the number Ri squared. It's just something. Any time that you could write a sum over mi times some formula sub I, you can replace that with an integral. So let's start by doing some analysis here. So if the rod has length L, capital L, by the way, this is the Greek letter lambda. It's like a lamb and then da. If it has mass m, we can answer the question, or we can at least ask the question, what is its mass density? People will often say linear mass density, by the way. So I'll put that here. The reason they might say linear mass density is because normal density is kilograms per cubic meter. This is density in a single direction, so this would be kilograms per meter, hence linear. What is its linear mass density? Well, we know because of the word uniform, the rod has uniform density. We know that lambda is unchanging, i.e. the density at one point on the rod is the same as it is at anywhere else on the rod. So what we could do is we could just take the whole mass of the rod and divide it by the whole length, and that should give us lambda. But we could have also done the same with any length of rod and divided by with any amount of the rod and divided by the length of that amount. So this lets us answer how much mass is in a chunk of length L. So if you take just like, I don't know, 5 centimeters of the whole rod, which might be 2 meters long, what is the mass of that length? So M would be the mass of that length, and I'm going to draw a picture in a minute. This would just be the mass times the linear mass density. Sorry, this would be the total mass times the fraction of the mass that is equal, the fraction of the length. Let me just write it out and I'll explain. This would be capital M times L over capital L. So it would be the total mass, and then you would just multiply it by what fraction of the total length is the length that we're interested in. So like if little l was half of the total length, then the mass of little l should be half of the total mass, right? And so we can rearrange this and get L times capital M over L. But M over L is just lambda, so this is just lambda L. Now let me just draw a picture just to illustrate. So here's our rod. Let's just call this position down here x equals 0. And hence this position would be x equals L. We're going to have x running up plus x. Again, that's a coordinate choice. And so if we just look at a small chunk of that rod, of say mass dm, that mass, well, we need to figure out what the, let's look at a small chunk of that rod at position x. So this distance might be x here. That length, let's just call it dx. It's just this, let's call it dl, sorry. It's just a really small length of rod. We're going to eventually take the limit where it goes to 0 and treat it as infinitesimal. But for now, just assume it's a really small length. So for an infinitesimal length, dl, so a chunk of rod that has infinitesimally small length, what is its mass? Well, we know that its mass should approach 0 as the length goes to 0. But we should be able to write some sort of formula that tells us about in what way the mass goes to 0 in the way that the L goes to 0. So the mass, just like what we did up here, we would write that the mass of that chunk, which we're just going to call dm, should be equal to lambda times the length of that chunk. So it'd be lambda times dl. And so in this case, I don't know why I keep using the wrong variables. I should have really called this dx because the variable that we're using to go up the rod is x. Of length dl. So referring back to our picture, dl is just dx in the coordinates that we're using. So this would just be lambda dx. And so by rearranging this formula, we can get that lambda is dm dx. And in fact, this is a definition. So the linear mass density of any system is just the rate of change of the mass as you go along that system in a direction with respect to the direction that you're traveling in. So you can note that this has to be constant because as you travel up the rod in the x direction, the mass accumulates at a linear rate. If you go halfway up, you get half the mass. If you go the full way up, you get the full mass. And so that's a linear rate. And so we would get that the derivative of the mass should be constant. Now, we are running out of time, so I'm going to continue for a little bit more, and then I'll call it there. Yeah, that's fine. So how can we use this information about lambda to do one of the integrals? Well, for example, if we were just writing the sum as I goes from 1 to n of just mi times 1, this should just be equal to the total mass, right? So if the object is continuous, then that would just be an integral of dm. And that should also be equal, that should still be equal to the total mass. But the question is this is not an antiderivative. This is like a real number. So it has to have limits. And so what are the limits? Well, in this case, we're summing over the whole rod, but I don't really know what that means when m is our variable. So instead, what we do is we rewrite this integral as a spatial integral. We use a substitution. dm is just lambda dx. And so what that implies is that an integral over the whole rod of dm, that should just be equal to an integral over the whole rod in terms of x. So it'd be an integral from 0 to L, because that's like we're changing variables from m to x. So the whole rod corresponds from x equals 0 to x equals L. And then we can use this formula up here to figure out what dm is in terms of dx. It is just lambda dx. And so we can just do this integral now. Lambda is a constant in this case. So this would just be lambda L minus 0, which is just lambda L. And we know what lambda is. Lambda is m over L, right? So this is m over L times L, which is just m. And that checks out. This is supposed to be equal to the total mass of the system. Now, that's fine. One of the integrals that we had to compute was the integral equivalent of this sum, figuring out what the denominator is when n goes to infinity. But if we want to find the center of mass, say the center of mass in the x direction, we'd have to do this top integral too, or that top sum as it becomes an integral. So let's do that. So the center of mass in the x direction, again, referring back to this rod here, in terms of integrals, this can be written as x dm divided by the integral of dm, and the limits of integration are over the whole rod in those cases. And so what we can do is we can just use the substitution where dm is lambda dx. So this becomes an integral from 0 to L of x lambda dx divided by an integral from 0 to L of lambda dx. Now we already know that this denominator just becomes m. But we can do the numerator. It's an integral of lambda x, where lambda is a constant, so it's just linear, so it becomes 1/2 L squared minus, 1/2 lambda L squared minus 0 squared divided by m. And so we can rewrite this. This is 1 over m times m over L, because that's what lambda is, times L squared over 2. And that is just L over 2. And that checks out too. For a uniform rod, a rod that has its mass evenly distributed, we expect the center of mass to be in the middle. And that's what this is telling us. It's telling us that the x position, like the x coordinate position of the center of mass, occurs when x equals L over 2, which is halfway up the rod. Now we're out of time, so I'm not going to continue here. But on Friday, we will continue with a slightly harder problem. We're going to then assume that the rod is not uniform, and then see what happens, and see how that affects things like the center of mass, and eventually we'll get to computing the moment of inertia. All right, so I'm going to end it here.